Hello everybody and welcome to the NPTEL online certification course on microelectronics devices circuits. In our previous module we had looked into differential amplifiers and we will start off from where we left, and let us look at the transfer characteristics. As we discussed in the previous turn, that if you go to extreme, this is basically the plot between collector current, normalized electric current with respect to difference voltage, normalized with respect to the thermal equivalent voltage, which is Vt 25 millivolts. If you go to extreme right, as you can see, you will see that the Q2 will be basically off and therefore the current will be 0, whereas Q1 will be on and therefore you will get a large current. So, this is Q1 is on, right. On the extreme left, Q2 will be on and therefore you will get Q2 a high current, whereas Q2 will be off and you will get a current. Somewhere in the middle where a linear region has been maintained is the region where the differential of current with respect to input differential voltage. So, this is basically, if you want to find out the slope of this curve from this point to this point, this point to this point, it is basically del IC by del VID, right. So, if that is the slope you are referring to, del IC by del ID is maximum somewhere in the middle of this region, right, somewhere in the middle of this linear region. And if you look very carefully, this is nothing but the transconductance of the transistor. So, this is transconductance. Why is it transconductance? Because you are giving onto the base the voltage, the difference of the base, and IC is the difference of the collector current. So, it is basically GM for the whole differential pair. For the whole differential pair, this is the GM which you see, transconductance. And as you can see, this is the region where GM is almost linear and therefore GM is almost independent of VID, right. GM is almost independent of VID at this particular point, which means that take any value of GM any point, at any point you bias your device and give you a peak to peak swing between this point and this point, and you would expect to see your GM to be almost constant and therefore gain to be almost constant, and the highest gain also you will get here. As you move towards this region or this, for example, if you look at this point, the gain will be almost equals to 0, right, because the current is not changing with respect to the variation in the differential voltage. Similarly, here the gain will be slightly less, but as you shift towards the middle where you have a linear region of operation, you get the highest gain, right. And therefore, I am also assuming that approximately alpha is approximately equals to 1, which a basic assumption I am taking here. To improve this linear regions, the problem is, if you look very carefully, the problem is that the linear region is only restricted by this much amount of VID, hardly of the order of few millivolts, right, few millivolts. So, typically if you want to make it more realistic differential amplifiers, you have to increase the linear region of operation, which means that you want to increase this one, you need to increase it, right, and make it shift, go to both right hand side. How do you do it? Well, the methodology which people adopted was that they inserted a resistance Re in series to the emitter region. And if you plot therefore the graph between IC by I, which is basically collector current normalized with respect to total current versus VID by Vt, the same graph as the above, you see as the Ri value becomes larger, right. So, this is for various values of Ri, this is the value with Ri equals to Re equals to 0, right. This is with certain value of Re such that I into Re is 10 times Vt, and this is with the value I into Re equals to 20 times Vt. So, obviously, this is suppose R1, Re1, Re2 and Re3, then Re3 is greater than Re2 is greater than Re1. In fact, Re1 is approximately equals to 0, you shorted it, the previous one, which means that if you look very carefully, you have actually increased the linearity. Look at the point that when you increase, when your Re3 is largest, your linear region is extending from maybe from this point to a larger extent, right. So, your linear region is extending. So, you can play with this for a large linear region, whereas when you make Re equals to 0, your linear region is very small, maybe this just small around, as I discussed in the previous slide. And therefore, in putting Re, we will discuss why is it like that, but increasing Re makes the linear, it is more linear, but the cost you pay for it is that the transconductance and the gain therefore reduces when your Re is large. We will also explain this point one by one. But as you can see, the slope here around this particular point, around middle when VID equals to 0, is small slope as compared to a slope of this line. So, you see that putting Re makes my linear region of operation broaden, but the cost I pay for it is that I reduce my overall gain. So, GM reduces, transconductance reduces. Why does it happen? We will just discuss that point. Say you have inserted Re here, right, you have inserted Re. First let us see why transconductance and therefore your GM reduces in this case. See, once you reduce, when you put Re, your Re actually has a bias which is something like this, right, and therefore in a sense it is reverse biasing your NPN transfer emitter base junction. So, I have an emitter base junction, if you give it is an NP N. So, if you give a positive potential on the N side, you are reverse biasing emitter base junction, and once you reverse biasing it, what does happen? The gain falls down, because you are not letting the large amount of emitter current to come across, and therefore your collector current will be also small. That is the reason your gain starts to fall down when you insert Re, right, and that is the reason your gain, and therefore you see your GM values are reducing, gain starts to fall down. Why does it increase the linear region? Because if you remember, gain bandwidth product is always constant. So, therefore, when the gain falls down, you can work with a larger bandwidth, your bandwidth increases, and therefore your linear region of operation becomes larger and larger in this case, right. So, that is the reason why we use so we can use this to generally make it this thing. Please understand, all these discussions are with the tacit assumption that both the arms here, left arm and right arm, are exactly symmetrical in nature. If they are not, then this does not hold good, there will be some changes which you need to do. Okay, let me come to the small signal characteristics of the of a BJT, of a bipolar transistor as a differential amplifier. So, I have Q1, Q2 here. I also have VID. VID is basically the difference in the potential of base to emitter of Q1 and Q2. So, if I see VB1 is nothing but VB is the basically the DC bias which I have applied, plus VID by 2. So, if the difference is VID, then if I write this to be as plus VID by 2, then this should be minus VID by 2. Why? Because VID by 2 minus of minus VID by 2 will give you plus VID, right, and that is the difference which you see here. That is the reason we write plus VID by 2 and minus VID 2. Similarly, we can write IC1 to be equals to alpha times IE1. Now, IE1 was nothing but I upon 1 plus e to the power minus VID by Vt, and IC2 will similarly be alpha I upon 1 plus e to the power exponential VID by Vt, right. Now, if you multiply the numerator and denominator for this transistor and this one by e to the power VID by e to the power 2 Vt, we get IC1 to be equals to this much, right, and IC1 we get is, and therefore and if we assume that VID right is much smaller as compared to 2 Vt, which is typically is, let us assume, we may expand the series in exponential, this one is in the numerator and in the series, and take only the first two terms. So, what the first two terms will be, I will just discuss that in the next slide, but assume this to be as the IC which is available to us. I get alpha I e to the power, so multiply VID by 2 times Vt, and then I multiply this to the power e to the power VID by 2 Vt, plus if I by 2 Vt, I will get minus Vd by 2 Vt, right, and therefore that is what I am doing here. If you look therefore on this side, on the base side, I get VCC minus alpha I by 2 into RC. Remember why? Why is it minus alpha IC by 2? The reason being that the total current flowing through RC on the left hand side will be nothing but alpha I by 2, which is the DC bias which you see. We have already discussed this point earlier, plus GM multiplied by VID by 2, because VID by 2 is the approximate voltage which is visible between base to emitter, that you multiply with GM, you get the current. So, this is what you get IC, but on the right hand side you will get a minus VID, because you see this is minus VID by 2. So, I get minus GM into VID by 2, right, you get minus GID by 2. Now, quite interestingly, if you simply add subtract these two, alpha I by 2 and alpha I by 2 cancels off, and what you get is basically GM times VID. So, even without knowing anything, if you just simply find the difference between this and this, the current difference, this is delta voltage difference, sorry, delta voltage difference which you see, right, and you get delta VIC which you see. Now you see, so what I get if we closely therefore come to the point, then I can simply so if you look from the right hand side, I can simply multiply it VCC, right, minus alpha. So if the potential drop across RC I need to find out will be nothing but VCC minus alpha I by 2 into RC, right, that is the potential which is appearing across RC, minus GM RC VID by 2, GM RC into VID by 2, right, because you have to subtract this voltage to achieve the voltage at this particular point. Similarly, if I get this, I have to multiply this with RC, and therefore I get VCC minus alpha I by 2 into RC, alpha I by 2 into RC plus, why plus, because there will be a negative sign here. So minus into minus is plus GM RC by VID by 2. Now if you subtract this from this, this whole thing gets cancelled with this whole thing, this remains. So this minus of minus this will give me GM RC into VID, fine. So the output voltage difference between the two is nothing but GM RC into VID. So this is del V out is equals to GM RC into VID. So if your VID is large, you get a very large value of delta V out. If your GM is large, you also get a very large value of V out, and this is true also we have understood from our basic understanding previously. Now let me find out what I was discussing with you in the earlier sense, that IC1 therefore can be written as this by expanding it, by expanding the previous discussion, and similarly IC, and therefore if I break it down I get alpha I by 2 plus alpha I VID by 2 times 2 VT, and IC2 is equals to alpha, IC2 is equal to alpha I by 2 minus alpha I 2 VT by VID by 2. So if you add these two together, so if I take IC1 minus IC2, as I discussed with you, you will get this will get cancelled out, and they will get this will get added up, and you get alpha I by 2 VT into VID you will get, fine. That is basically the difference in current. This multiplied by RC will give you the difference in voltage. Now you see very well that this is nothing but the transconductance of the device GM, and therefore we can safely, so that is what I am saying, IC by VT is the transconductance of the device, and therefore I can safely write down this to be as GM times VID into RC, which we have already derived in our previous case, right. Okay. So this gives me an idea about the basic understanding, and therefore as we have already discussed that the transconductance of a device, higher the transconductance of the device, more will be the output voltage, higher the value of RC, more will be the value of V. So this is basically your del V out which you see, right. If you look at this graph here, and what I am trying to tell you here is, if you look at the figure here, you see that Q1 and Q2 are both in active region of operation, and if we now try to find out how much amount of input resistance is there. See, when you are looking at MOS devices, MOS based devices, right, in the MOS based devices you are actually looking into the gate side, the signal was inserted to the gate side of a MOS device, which is obviously giving you an infinitely large input impedance, because gate was having a dielectric constant of oxide, and therefore this was a problem. Whereas in this case, which is in this case, you are actually looking into the base side. So base side will have a finite resistance, and there that is what we are trying to find out. How do you find out? You find out the base current, right. So base current, if you want to find out, if it was basically a basic idea that if the resistance looking from the source side is, let us suppose, twice Re, right, then on the base side it will be B plus 1 times Re. So that is what I am trying. So you have to multiply by beta plus 1 when you are looking from the base side. So the base current will be VID by 2 Re into beta plus 1. Similarly on this side, so where VID by 2 Re is the difference voltage which you see in front of you, therefore if the same current flows through, so alpha times VID, so current is basically VID by 2 Re, that is emitter current. If you multiply by alpha, that is collector current. So this is the collector current here, and this is the collector current here. If you multiply this with RC, I get the voltage at this particular point with a negative sign, and since they are 180 degree phase shifted, I will get a positive voltage here, which is alpha VID by 2 Re into RC, right. And the base current will be VID by 2 Re. VID by 2 Re is nothing but emitter current divided by beta plus 1. So IB equals to emitter IE upon beta plus 1, remember, and from there I get this as the emitter current which you see, right. Now with this region I said IC equals to alpha IE and IE therefore equals to VID by 2 RE plus 2 RE we get. So the input differential input resistance RID is equals to beta plus 1 into 2 RE, right, and this beta plus 1 into 2 RE is also referred, this is R pi and therefore we refer to this as RID is equals to beta plus 1 into twice RE. RE is the resistance looking from the emitter side, right, and the differential gain is GM times RC. GM we have already found out to be some value which is RC by RE plus RE, right. RC, how do you find out differential gain? If you want to find out this will be this you need to multiply with RC, right, you multiply with RC you get the V out. Now this VID if it goes down I get VO by VID, right, I will get RC upon 2 RE plus RC. So this 2 will be very small as compared to anything else, I get RC upon RE plus RE, right. RE is the resistance offered from the emitter side and RE is the DC resistance which you have actual resistance which you have put. So if you see a differential gain depends upon the ratio of your collector resistance to that of the emitter resistance plus the RE value. RE value is the small signal RE which you see. So it is basically 25 MeV millivolt by IE, this is equals to RE, right, and this is what we get as the differential gain. Now the concept here is that if everything is symmetrical, both the left arm and right arm are symmetrical, we can divide the whole differential circuit into 2 half circuits. So what we do typically is that we break it down this middle and then we say that on the left hand side VID by 2 is the input voltage, on the right hand side it is VID by minus 2 voltage and they are biased such that I by 2 current flows through this arm and this arm and therefore VOD by 2 at this point and VOD by 2 at, so minus plus is there, right, and therefore the output difference, if you find the difference between the two it will be still equals to VOD. So this is the concept of differential half circuits, that overall transconductance will be divided by 2, you will also have the bias current divided by 2 and you what you do is that you emitter part of the BJT is actually grounded here, right, they are grounded here and once they are grounded they act as a differential half circuit, right. The advantage is it is much easier to calculate various formulas from differential half circuits. With this knowledge let me therefore come to a small signal characteristics of the differential amplifier. As you can see my input voltage I have already told you is differential VD by 2, right. So I am giving VD by 2, this R pi is nothing but the input side resistance offered by the differential pair. So it is basically the pairs R pi, right. If you look at the right hand side, since it is a VCCS voltage controlled current source, any V pi which you give in the input side you will have GM into V pi as the current flowing in the output side, right. So this is your this is your collector resistance which you have already found out and R0 is the resistance offered by the device itself, right. So these two are in parallel. So if you even close your eyes, do any problem, I simply can get the differential gain to be equals to GM times RC parallel to RO, right. So transconductance multiplied by output impedance will be actually equals to the voltage gain and that is what we have shown here, right. This is with the assumption that my REE which is the so what I have done here is that I have replaced the current source by a resistance and this resistance value is very large, it is typically very large, right, and it does not let any current to flow through it typically and therefore I can safely write down VE to be equals to VID by 2 which you see here, VID by 2. So the emitter resistance, so emitter voltage is exactly equals to VID by 2 in both the cases. Let us look at the common mode gain and CMRR. What we will be doing and what we will be understanding is basically that let us suppose that in reality of course your left and right hand side will never be symmetrical with respect to each other, that we already know. Because there will be some mismatch in the resistances, some mismatch in the emitter resistances, some mismatch in the collector resistances, the transistor itself will be mismatched in terms of thermal equivalent voltages and so on and so forth. Now under a criteria that you do have a change, let us suppose that my one of the arms RC changes by delta RC, then I can safely write down VO2, you can do it yourself, is given by minus alpha times RC plus del RC upon 2 RRE plus RE into VICM. VICM is nothing but the input common mode voltage, right. I am not giving a differential voltage now. So under the presence of an input common mode voltage my output voltage VOC comes out to be this. So let us suppose there would not have been any delta R, so this would have been 0, this would have been 0, right, this would have been 0 and I would have got alpha RC upon 2 RE plus RE. Now, because of this delta RC I have an extra voltage term which comes into picture. Now, therefore, VOD, which is the output difference voltage, is VO2 minus VO1 will be given by this quantity. So, which means that even in presence of a equal voltage at the base of the two transistors, because of a delta R change in one of the resistances, I always will get a VOD equals to this value, which is given by this value. So, if delta RC say 1 ohm, then I will always get, so V in equals to, suppose 1 ohm, this is 1 volt and this is also equals to 1 ohm, then there will be an alpha upon 2 REE plus RE, right. Alpha is very close to 1, so I will get almost equals to 1 upon this whole quantity. RRE is very large quantity, so typically what I will get is VOD few millivolt, there will be always an offset available to me, the order of few millivolts. We define therefore ACM, which is basically my common mode, we define this to be as a common mode gain. Common mode gain is basically my output voltage under the condition that I am given a common mode voltage in the input side. I get this to be true, you see this VOD. So, so if you divide by VICM, this VICM cancels with this VICM and you are left with ACM to be equals to this much. Now, you can write down ACM to be also breaking up into this value, you just simply can do it small manipulation, and CMRR, which is basically known as common mode rejection ratio, is defined as the difference of the or the ratio of the differential gain to common mode gain, which means that if I give a common mode signal to both the arms of my bipolar differential amplifier, I record a gain, right, and that gain will be by virtue of delta R whatever change is there, and I also record a gain by giving a differential signal to both the arms. I divide one upon another and I should get CMRR. Ideally CMRR should be infinitely high. The reason you can understand why, because your ACM should be ideally equals to 0. Ideally your ACM should be 0. This we have seen during the first few slides of my previous lecture, that ACM should be approximately equals to 0. The reason being, for exactly the same bias applied to two transistors, the output was actually equals to 0. So, my ACM should ideally be equal to 0. It is not by virtue of the fact that both the arms are not symmetrical in nature, there is some difference. So, there is some finite value of ACM. Similarly, AD will be some particular value. So, if you divide AD by AC, I get this as my CMRR. So, it is 2 GMRE upon del RC by RC, right, and this gives you a value of your CMRR. RE obviously is very large value, GM is also very large, del RC is very small, RC is also relatively large of the order of kilo ohms. So, you get CMRR very large of the order of 10 to the power 5 to 10 to the power 6. Ideally you should get infinity, but this is the order which you get for CMRR. Higher the value of therefore the CMRR, the common mode rejection ratio, better the differential amplifier in rejecting common mode signals and accepting differential mode signals or amplifying differential mode signals, right. Typically you will see, as you maybe we can take up in the next slide or maybe in the next lecture, that noise is generally common to both the arms, noise is not differential. So, therefore, a differential amplifier will be a very good rejecter of noise and very good amplifier of signal, and therefore, higher the CMRR value of a differential amplifier, better the design is as far as its input resistance is concerned. Okay. Let me therefore explain to you what is known as common mode input resistance. We have seen it already, and it is resistance looking from the input side to the base side of a design, right. So, if you remember the half mode signal I divided by 2. So, if I take, so I will get RE, so I get RE, so I get 2 RE available to me, because this I am just overlapping with respect to each other, RC, and therefore I get VCM. So, RCM comes out to be just a definition, I am not deriving it in the class, but it is beta times RE upon 1 plus RC upon beta RO, and this is the value of your RE in CM. So, this is the input resistance. It is actually infinite in case of MOS differential pairs, but it will have finite value when you have this into consideration, right. Let me come to the multi-stage amplifiers. Well, in practical stages you will have maybe each differential amplifier driving another differential amplifier, so on and so forth. the first stage is usually, so if you have a multi-stage amplifier, typically the first stage is required to provide a high input resistance in order to avoid loss of signal level. So if you have two stage amplifier, the first stage is generally used to match the impedance. So the first stage has got a high input impedance, because typically my source has got a high output impedance. To match the two, generally the first stage is basically having high input impedance. In differential amplifier, the input stage must have very large CMRR, right, and therefore that is what I have written here, right. So the function of the middle stage of an amplifier cascade is to provide a bulk of the voltage gain. So if I have got 2 stages, 3 stages, let us suppose the first stage is just to match the impedance level, so that the maximum power is transferred. The differential part will be responsible for high gain by virtue of by noise rejection, by virtue of high value of CMRR, and maybe the third stage, the middle stage, will be responsible for high value of voltage gain, right. So we will come to that in a much more detailed manner. At this stage, this is just a diagram of a 2 stage op amp. We have just given an idea about in reality, because after this lecture we will do the MOS differential pair, and then it will become clear. Maybe we will revisit once more when we come to op amp later on. But if you look very carefully, this is nothing but a replication of the BJT differential pair. If you look very carefully, this is the differential pair which you get here, right, and this is the differential pair which you get here, where I am giving, this is the input differential R which I am giving here, and this is the single ended output which I am taking from this arm, right. So this pair is responsible for doing all impedance matching, this one is responsible for giving you a large gain, and this one is responsible for again impedance matching and giving you a proper output, right. So there are 3 stages, 1, 2, 3 stages here available here. Let us now look into this basic fact here. These are simple facts which you should be aware of. At this stage we will discuss our op amp maybe in details, we will come to revisit this formula once again. So just to recapitulate of what we have done till now, the first stage of any amplifier design is basically a differential amplifier, right, gives you a very high gain. As I discussed with you, differential amplifiers are insensitive to noise, they are very good rejectors of noise, but they are very good enhancers of the input signal. For perfect CMRR, common mode gain is 0 and CMRR is infinite, as I discussed with you. So if you want to use BJT as a linear amplifier, we apply a very small differential signal. If you apply a large differential signal, you might end up having a highly nonlinear profile available with you, right, because then you move away from the linear region. So you generally apply a small input signal, right. So this way we have actually taken care of the very basic understanding of a differential signal. We in the next lecture series we will take up MOS differential amplifiers, right, and then explain to you how is it different from a BJT difference amplifiers, and we will see that MOS is relatively slower in switching as compared to BJT, because in BJT, if you remember, one basic idea was we are moving from active to cutoff and vice versa, we are not at all moving to saturation. So once you do not let the device move into saturation, the time taken to come out from active to cutoff is much faster as compared from saturation to active, right, because you are in saturation you are storing large amount of charge in the base side which you have to first remove, right, and therefore it is much faster. So BJT based amplifiers are much faster as compared to MOS based, right. So but we will look into other factors as well. For example, power dissipation is however much higher in case of a MOS device as compared to in case of BJT as compared to MOS device, fine. With this I think we have finished with single stage amplifier basic understanding using BJT. In the next we will look into the single stage amplifier differential amplifier using MOS devices. Thank you.